Yeah, Mark.
All right, please go ahead.
Yeah. So yeah, thank you, Mark, for the invitation. So yeah, this work I did jointly with Cosmo, and I'm somewhere in between. I moved from being in Sheffield back to sunny Sydney. So currently I hold a fellowship with the Sydney Quantum Academy, which is a new initiative by the New South Wales government to build a local quantum economy. Anyways, so I guess the motivation for this work stems from some of these super resolution results coming from Mancade Zhang a couple of years ago. So I'll just briefly go over where that came from. So if you're not familiar with quantum metrology or quantum imaging, then this is a very brief overview. So as we all know from, first year, maybe not first year, like basic optics, if you try to image a distant point source, due to the fact that your lens has a finite spread, the image of the point source you have on the screen is not a single point, but rather it'll have a distribution. And so if you're using a circular lens, then this spread, which we call the point spread function that characterizes this distribution, would be a sinc function or the area disk. So 2 point sources, here you can see that they're resolved, and here they're getting close together. And for image C, they've merged into a blob. And traditionally for astronomy, 2 sources are considered resolved if the peak of one of the distributions lands further away than the trough of the other. Right, so, and the minimum resolvable angular resolution, minimum angular resolution is given theta, so that is this angular separation of the 2 point sources is approximately the wavelength divided by d, which is the diameter of your lens. So basically, the larger the lens you have, the sharper your point spread function becomes. Okay, so now if the goal is to resolve the distance between these 2 point sources from estimation theory, if you're doing classical imaging, then what is called the Fisher information drops 0 as the separations become close. So this practically characterizes the precision you can achieve by measuring this parameter. On the other hand, if you calculate the quantum Fisher information, that is something that's maximized over all possible measurement, then the quantum Fisher information actually stays constant all the way up to a 0 separation. So this is kind of hinting at the fact that if you do an optimal measurement, then you can resolve things which are very small with constant precision. And now, so what we thought was, if these techniques are very good at resolving things which are very small, smallly separated, maybe it'll also be good at detecting things which are very close together. So we thought, okay, what can we do with it? And one kind of obvious example would be to see if we can do something about exoplanet detection or improving exoplanet detection methods for over direct imaging. And this is why we want to consider perhaps improving direct imaging. So there are a couple of different methods used currently for exoplanet detection. So some of the more sensitive or traditional ways include transit methods. So these are the green square over here. So that's when you have a star making a transit in front of the planet, and there will be a temporal dip in the intensity of the star due to the fact that something that's dark is blocking it. Or you have radio velocity, which is looking at the motion of the star in response to something that's orbiting it. So you're looking at effectively the Doppler shift of the star spectrum. And then I think direct imaging is the third most popular method. But as you see over here, so this is plotting the mass of the planet that's been found. And on the other axis is the period. So transit methods and radio velocity methods are typically more sensitive to planets which are closer to the star, because you basically have to see them edge on. On the other hand, direct imaging has been traditionally more sensitive to planets which are in a further orbit, precisely due to the fact that you're trying to image something that's very faint next to something that's very bright, and it's difficult to resolve these. And I will mathematically quantify this statement just now. Okay, so now we can quantify the problem. So the problem is a hypothesis testing task. So you have two hypotheses, HA and HB, where HA corresponds to the null scenario, where you have just a star and no planet. And whereas HB, hypothesis B, you have the scenario where you have a star and within its proximity S, there is a planet. And the planet has relative intensity epsilon, and the star has relative intensity 1 minus epsilon. So here we're preserving the total photon number, just so that, well, okay, so if we do want to, in principle, this information NS is used, but we are saying that if we don't know what exactly the mean photon number is, we're going to collect n photons and see what we get, or what we can get out of, what information we can get out of the system. So of course, classically, if you're looking at a photon distribution on the image screen, this is what it will look like for H0, and for H1, you have something that's, you know, a big peak next to a smaller peak coming from the planet. And of course, quantumly, these two would correspond to two different quantum states. So we are trying to distinguish between these two probability distributions classically, or these two quantum states quantumly. Okay, so now we can frame this in the context of quantum state discrimination. So for quantum state discrimination, there are two fundamental results. So we have the symmetric case, where we're trying to minimize the total probability of error. So we're minimizing the probability of false positives and false negative simultaneously. And this is given by the trace distance, and the relative quantity to consider is the quantum Chernoff bound. So the probability of error takes this form, where n is the number of repetition of the experiment, or the number of photons that you detect, and the error exponent is dictated by the trace distance. So, however, but for certain scenarios, such as the exoplanet case, we might want to look at the asymmetric case. So why do we want to do that? So since exoplanets are rare, we might want to accept a certain probability of a false positive, and so mistaking the planet to be there when in fact there is a vacuum, but because they're rare, you don't want to miss it. So the question we want to quantify is, how do we so what is the probability of error, what's the probability of missing the planet? That way. So given that the planet is there, what is the probability of mistaking it for the vacuum? And that question is answered by the quantum Stein lemma. So it states that the probability of error is given by the negative of exponential of n times the quantum relative entropy. And the quantum relative entropy takes this form. So you have trace of rho 0 multiplied by the difference at the eigenvalues of, that should be rho 0 there. Yeah, rho 0 minus rho 1. So this is the case we're interested in right now. So another motivating problem would be, so for example, for COVID testing, you might be much happier to tell somebody who's innocent to stay home rather than missing somebody who's infectious and let them know around the community. Right. So the quantum relative entropy is what we're going to be concerning ourselves with for the rest of the talk. Okay, so now we can talk about the density matrices for these two different cases. So for the null hypothesis, we have NS photons, or a thermal state of mean photon number NS coming from just a star. And so rho 0 looks like this. And for hypothesis 1, you have with intensity 1 minus epsilon, a photon that's coming from the star, with plus with some small probability epsilon, where the photon is coming from a planet, and this is slightly shifted. Right. So let's first consider the case where at most a single photon arrives on the image screen, because that's much more intuitive. So now we can calculate their on-screen probability distributions as a function of x, which is position on the screen. So here we're going to approximate the point spread function as Gaussians. So of course, in reality, you might want to model these as array functions, but the Gaussian approximation works pretty well most of the time. So these are the classical probability distributions, and we can go ahead and compute the classical relative entropy. And because the classical relative entropy, i.e. the error exponent, sits inside the negative of an exponential, we want this quantity to be large. Now, if we calculate the classical relative entropy of these two probability distributions, it scales as s squared and epsilon squared. So this is quadratic in both the separation between the two sources as well as the relative intensity. So if both of these parameters are small, then the classical relative entropy is also very small, and that quantifies why detecting a faint object next to something that's bright is very difficult. Right. And now we can go ahead and calculate the quantum relative entropy. But before we can do that, because the wave function of the planet may not be orthogonal to the star's wave function. So remember, there's a finite overlap spatially. We have to find a suitable set of orthonormal basis set that spans the Hilbert space of rho 1. And we can do this by using your typical Schmidt orthonormalization methods. So you will take the difference between these two. So I think you take the overlap between these two. So the star's wave function and the planet's wave function, you take the overlap between these two and you take a difference. So if I go ahead and write the density, these two density matrices in these spaces, then it kind of looks like this. And now calculating the relative entropy for a 2x2 matrix is a very easy task. And I can go ahead and show you what the relative entropies look like. And they look like this. So one thing to note is that in the limit that epsilon, i.e. the relative intensity is very small, the quantum relative entropy scales as s squared times epsilon. So we've gained a factor of epsilon between the classical and the quantum case. So I've been told that this is very exciting by astronomers because there's epsilon is typically very, very small. If you look at real exoplanets, so they are definitely less than a couple of percent. So I can go ahead and plot these. So the green curve on the epsilon dependence graph is given by, so you can see that there are two, different scalings for these two quantities. So clearly in the low epsilon limit, you can see the epsilon dependence showing up where this has a shallower slope. And now on the other hand, I can fix epsilon and plot the difference as a function of the separation parameter S. And as you can see, for all values of the separation, there's a clear quantum advantage until the two sources become very spatially separated. So when you can clearly resolve these two on the image screen, doing something quantum is not going to help you, but that's kind of very intuitive. So, okay, so you're not going to believe me unless I show you a physical measurement. And this is what a physical measurement could look like. So I think I'm going to talk about this device first. This is what Zhang et al. Termed spatial demultiplexing. So what this is physically a multimode fiber, and inside the multimode fiber, there are these natural Hermite Gaussian modes. So for Q equals to 0, it's the first order Gaussian, and for Q equals to 1, then you get a positive and a negative dip, and so on and so forth. So what you want to do is to take the weighted center of the system you're trying to image. So that takes this form over here. So if the planet is sitting at position x0, then the weighted center would be given by this expression over here, where you have 1 minus epsilon, the intensity of the star, multiplied by its position, plus epsilon, the intensity of the planet, multiplied by the planet's position. So you take the weighted centroid and you feed it into the center of the spade device. So in the ideal case, if only the star is present, then the light that's collected by the lens would only couple into the fundamental mode, as opposed to when the star is present, you will start having the higher order modes excited. So when you see that happen, you know that something's present. So another method would be something that they called silver, also termed by Zhang. So here you would take, once again, the centroid of the object, put it through a beam splitter, apply a phase shift on one side, and then and have a second beam splitter. And what this tells you is that whether the image is central symmetric or not. So both of these would work in principle. Okay, so far we've considered the case where we have a single photon arriving at the time on the image screen, but in reality, the system we have are thermal states. And of course, we can go ahead and describe the thermal state with the Gaussian state formalism. So we can write down the covariance matrix of the thermal state. And once we have that, there is this nice result over here, which tells you what the quantum relative entropy is for the two states. And I'll just show you what it looks like on a plot. So here we're plotting the relative entropy per photon as a function, as a function of the mean photon number and the separation. So if you do the actual optimal measurement, this shows that the quantum relative entropy does not decrease that much, even when you go to ns equals to 500, which is a ridiculous number for a thermal state. So if you look at real astronomical sources, the mean photon number is typically very small. So yeah, so it drops by a small factor, but not that much. So we can consider the spatial demultiplexing measurement again. Once again, it's still fairly optimal in the limit of small epsilon and small separations, but its optimality does drop off quite a bit if you increase the mean photon number. Okay, yeah, so in conclusion, we've calculated the type 2 error probability exponent of a state discrimination case where we want to discriminate between having one or two sources of arbitrary intensity. And we found that in the limit that the relative intensities are very small, the quantum relative entropy is larger than direct imaging by a factor of 1 minus epsilon. And we also have two optimal measurement methods that is optimal. Yes, so here's the archive link. It's actually coming out to PRL today or tomorrow, I've been told by the publisher. Yeah, so to the future, we want to look at what happens if we have access to the quantum internet and use the quantum internet as a huge telescope array. So we want to establish long-term optical coherence through an entanglement assisted network. We might want to implement some of these quantum error correcting codes to combat loss. And then we have current active collaborations at Bristol, Herod-Watt, and Erlangen, and we're open to further collaborations. Yeah, and just before I left the UK, I wrote a grant with Peter together and we were successful. So now somebody else is being hired on the grant. And I thank you for your attention.
All right.
So questions?
Thank you for a nice talk. Any questions for Zixin?
Yeah, I get you talk about this type 2 error probability. I assume that you've got a composite alternative hypothesis in the sense there's many different possibilities for epsilon and many different possibilities for S, the separation.
Yes.
Do you have like a single good guess, or do you like is the type 2? I guess the type 2 error probability is sort of a function of these parameters. Yeah.
So like the single question that we're answering is, do we have a planet or not, right? Mm-hmm. And obviously, if you have two distant point sources, as they become close together, they become harder to detect. Mm-hmm. And if this source gets fainter, that's also harder to detect. So your probability of error would depend on how close they are together and how bright the second one is. And so these are the expressions, and we can calculate exact form of the quantum relative entropy. I don't think you need to know what epsilon S are in advance. Because because you don't need to use it in the measurement.
So when you
implement, sorry, I'll interrupt. When you implement the spade or silver measurement, you don't need to know epsilon, right?
Well, you don't. That's right. You don't need to know what epsilon is, but I guess when you have to know something, and that is just the weighted centroid of your system. Mm-hmm. And I spoke to an astronomer, and he said that in some sense, the weighted centroid is the only thing you can measure, because if they become close together, then everything's a blob. Then you don't know whether something's there.
So you do like a pre-measurement, you point it right at the middle of
exactly
wherever it tells you to point it.
Yeah, so obviously if nothing, like if out of the 10,000 photons you collected in your pre-measurement stage and nothing came from the star, then you would point it at the star. I guess that would still work. Yeah.
Seems to me, yeah, it's interesting. It seems to me like, suppose you did this, and theoretically, if there's no other planet, you should see everything in the queue equals 0. and
Yes, that's
nothing in
right.
those higher modes, right?
That's right.
Seems
Yeah.
to me like maybe if you do start seeing things in those other prior modes, it seems to me like where you're seeing things in those other higher modes might start giving you like a point estimate for what epsilon and S are or something like that.
That's right. Yeah, that's exactly right. But I've also been told that to try to line everything into the fundamental mode is almost experimentally impossible. So
yeah. Okay.
yeah.
So maybe a comment I'll make is that if you delve into the proof of the Stein's lemma, then indeed, the measurement, like you're in the context of the Stein's lemma, you're allowed to know as the receiver the mathematical description of the states rho and sigma, and then you're allowed to design a measurement based on that information. So in the Stein's lemma, the optimal measurement will depend on epsilon. However, you investigated actual measurements and how they would perform, and then you're comparing to the ultimate limit. And so that's interesting to see. And it's very interesting that it does essentially near optimal, I guess, because like in the Stein's lemma, the receiver is allowed an arbitrary fault tolerant quantum computer, right, that can do like collective measurements, right? And you can still show that this much more practically realizable scheme gets very close. So that's great.
It's almost optimal, but not quite. So I don't know how to get to the like 100% there yet.
Yeah. So another small comment is your archive link. I think it must be wrong because it had 12 at the beginning.
Oh, sorry. I
on your that's probably fine, but then on the final slide.
Oh, whoops. Okay. Anyways, it's on my. Right. Oh, there we go.
Okay.
9 years for the editors to accept it.
So then, did you look at the Chernoff bound at all, or you just? It seems like you focus exclusively on relative entropy. Right?
Yeah. So that's when the honest behind the scenes come out. This is where it comes out. So I actually looked at the quantum Chernoff bound to begin with, and I found that the quantum improvement was like a constant factor that's fairly small. So I'm like, let's look at the other one. I'm like, oh, the other one's great. Let's stick with that one.
Interesting. Yeah. There was a paper of mine that you cited on quantum illumination. And that was where we were surprised to find a significant increase in performance when you look at asymmetric versus symmetric. And I actually don't quite know why that is. It was just something we found. So it's interesting to see something similar happen, I guess.
Yeah, I can give you, I think I'm up to time, right? But I can give a sort of, wishy-washy argument as to why we shouldn't look at the first case, because the probability of these planets are very small. So if that's your prior and you want to, minimize the total probability of error, then if you keep guessing nothing's there, then with very high probability, then you're always right. So I guess it's probably more important to consider the second case anyway.
Can I ask a quick question on that? So I'm not very familiar with Stein's lemma, but for this prior, I mean, your prior can vary. So it seems like we've got the symmetric case and we've got the asymmetric case, but it doesn't take into account the degree of the prior. So should there be a sort of sliding spectrum between them to take into account the prior?
Oh, I am not entirely sure how to answer the question. I actually don't really know why there's actually a difference between these two, but it just pops out.
Okay.
Yeah, I don't know. Yeah, I don't know.
Found in the Stein's lemma then.
I believe there was a recent paper of Nilanjana Datta and Robert Salzman where they addressed this kind of thing, like interpolating between asymmetric and symmetric, and they had some interesting information quantities arise.
Okay, cool.
All right, so we are indeed.
I have a simple question.
Yeah, go ahead.
The difference between the classical epsilon squared and the quantum epsilon should we think of it as that one is, of course, dependent on the square, the probability, and the other one is like a cross term between the epsilon and 1 minus epsilon? It's an interference-like. It's an interference-like term.
Yeah, so an intuitive way to understand it would be to say, because if you work, so when you're doing the perfect measurement, you're kind of working with the electric field directly, right? Whereas the other one, so with the phase sensitive measurement method, you're working with the electric field, whereas the direct imaging, you're working with intensity, which is the square of the electric field. Yeah.
Right.
Really quick, you said mean photon number was usually around 1 or 10. I mean, what does that mean? I mean, you point a telescope and you leave it on all day, you'll get thousands of photons. Is there some like window of measurement or something? Or
yes. So if you look at a reasonable acquisition time, whatever that means in astronomer terms, for a quasi monochromatic light, because what you see from a star is very broadband. So if you just look at a very narrow frequency band, that mean photon number is very small.
okay, so they have like a
All right,
preferred.
so I think as the host, I should interrupt now to keep us on track for time for the day. So very interesting talk, clearly many more questions, and you can email with Zixin or find her on Twitter. All right, our next speaker, I believe, is Zoe. Is that right? I should actually look at the, yes, okay, good. So Zoe Holmes is currently a postdoc at Los Alamos, and she will move to start a professor position at EPFL in Switzerland. I think fall 2022, if I'm not mistaken. So Zoe has collaborated with some of our group members. You know, Kunal Sharma went to Los Alamos, worked with Zoe. And then this past summer, Aliza Siddiqui, who's been working with our group, has done an internship with Zoe. And so we're very happy to have her here or you know, remotely present her work about NISQ algorithms. Please take it away. Actually, I should hit stop recording. I forgot to do that.